Welcome to Chapter 13 of MEC410, Design of Machine Elements. This week we're going to study tolerances. We have 4 homework problems for you to do, a couple of hints for the last one. In Chapters 7, 8, 9, 10, 11, and 12, we discussed how to specify pulleys, sprockets, gears, and attach them to shafts and then design the shafts. In Chapter 13, we will discuss how to fine-tune the mating dimensions of all parts by specifying tolerances. And then you'll be able to put the tolerances on a drawing of a shaft, such as the one shown on this slide. There's always statistical variance when manufacturing mechanical parts, and the mating diameters of the parts must have proper tolerances for interference or clearance fits. Common interference fits are found in bearings and high-speed rotors mounted to shafts. And common clearance fits include balls within a ball bearing housing, gears, pulleys, and sprockets on shafts. Here's an example of interference fits. You can have a press fit, as shown here on the left, where the interference is created because this shaft is larger in diameter than the hole into which it is pressed. Or you can have a taper fit where interference is created when the fastener is tightened so that the parts are drawn together. And one hallmark of a taper fit is that the side walls of the shaft and the hole are at an angle, which is different than this shaft, which is perpendicular to the plane of the hole. And you can have a shrink fit where the hub, which is this part here, is expanded with heat, or you can shrink the shaft with cold before the parts are assembled, and then when the parts come back to room temperature, interference is created. Here's some tolerance definitions for you. A unilateral tolerance deviates in only one direction from its nominal size, while a bilateral tolerance deviates in both directions. The total tolerance is the difference between the maximum and minimum dimensions allowed. You get a positive allowance when you have minimal dimensional clearance between mating parts, and a negative allowance when you have minimum dimensional interference between the mating parts. And the fit is a measure of the looseness or tightness of the parts once they're assembled and given the full range of possible dimensions per the tolerances. Let's do a few manual calculations of clearance and interference fits. This problem comes to you from chegg.com, which is a popular website for engineering problems and solutions. Here we have a bilateral tolerance where we have to find the max and minimal clearances. The dimension of the pin here is 0.9980 plus or minus 0.007, and the dimension of the hole is 1.006 plus or minus 0.0007. And when we find maximum clearance and minimum clearance, we see that it varies from 0.0040 inches to a minimum clearance of 0.0012 inches. We can calculate the unilateral tolerance for clearances. Here is our pin dimension. It's from the outside of these two pins, 1.3004 plus 0 minus 0.0007 thousandths. And the hole is 1.3010 plus 0.0007 minus 0. And the maximum and minimum clearances are smaller numbers, from max of 0.0020 inches to minimum of 0.0006 inches. We can find the unilateral tolerance for an interference fit, where the shaft has a dimension of 1.6250 plus 0.0005 inches minus 0, and the hole, here's the hole, is 1.6232 plus 0 minus 0.0005. And we find the max interference is 0.0028 and the minimum interference is 0.0018. And we can calculate a bilateral tolerance for max and minimum interference. Here's the pin 0.5967 plus or minus 0.0003, and the hole is 0.5952 plus or minus 0.0003. And then the maximum interference allowable is 0.0021 and the minimum is 0.0009. The ANSI ASME standard B4.1 specifies 9 different clearance fits for classes of mating parts. They vary from RC1, which is a close sliding fit, about as close to interference as you can get without actually being interference fit, all the way to what's called a loose running fit, RC9, where the parts are mated, but they wiggle around a lot if you think about how loose these numbers are really going to get. And all the other clearance fits are somewhere in between. Our textbook gives dimensions for RC2 sliding fit, RC5 medium running fit, and RC8 loose running fit. So we'll use those in all our homework problems and exam problems. The 3 clearance fits are defined in Table 13-3. The way you read the table is you find your nominal shaft and hole dimensions where they range. That tells you what row you're on. Then for a particular row, you have the RC2 fit, RC5, and RC8. And then you are given how to dimension your hole and your shaft in thousandths of an inch tolerances. So if it says plus 0.6 here, that means plus 0.0006 inches. Same with the minus. Suppose we have a nominal 1-inch hole and we want to go with an RC2 clearance fit with the shaft. So 1-inch hole is somewhere between 0.71 and 1.19. Then the limits of clearance for that hole are between 0.3 thousandths and 1.2 thousandths. The hole gets the nominal size of 1 inch exactly on the negative side. On the positive side, it's 1 inch plus 0.0005. We'll give you an example on the next slide to fill in all the numbers for you. Here is a RC2 clearance fit for a 0.125 diameter shaft and hole. 0.125 always in between 0.12 and 0.24. The maximum clearance between the hole and the shaft is 0.00065 inches because it's 0.65 times 0.001. And the minimum clearance is 0.00015 inches. That makes the hole size 0.125 inches. On the plus side, it can be 0.003 higher. On the minus side, it's 0. And the shaft is 0.12485 plus 0 minus 0.002. And that comes from the fact that the nominal shaft size on the minus side relative to the 0 for the hole has to be minus 0.15 less than the nominal hole size. So you take 0.1250, you subtract 0.00015, and that gets the nominal shaft size, 0.12485. Can't be any bigger than that. And the difference between minus 0.35 and minus 0.15 is minus 0.2. multiplied by 0.001, such that the negative tolerance on the shaft is then minus 0.002 inches. Figure 13-4 gives you the RC fits for basic hole sizes of 2 inch, showing tolerances for the hole in the shaft and the minimum and max clearances. And what this chart basically says is that for the RC1 fit, which is the closest running fit, the dimensions that vary from the basic hole size are very small because you don't want the shaft and the hole to differ by very much because you want them to fit tight, not interfere, still clear, but not by much. As you go higher up through the classes, the difference between the hole size and the shaft size keeps getting larger and larger and larger. And not only that, but the variance allowed for the hole and the shaft sizes gets larger and larger. And the variance for any one clearance fit is the height of the bar, which tells you what is the max to min size of the hole. Say where I'm pointing for RC8 gives you the tolerance of 0.004 as a difference between the fact that the shaft could be 6 thousandths below the nominal hole size or 10 thousandths below. Here's an example in problem 13-1. They want us to specify the class of fit, limits of size, and limits of clearance for the bore of a slow-moving but heavily loaded conveyor roller. It has to rotate freely on a stationary shaft under heavy load, and the nominal diameter of the shaft is 3.5 inches. Use the basic hole system. We've chosen a class RC5 for this application. Gets us fairly accurate machine parts for higher speeds and or higher loads. And our nominal diameter of the shaft is 3.5 inches, which is between 315 and 473. So we're operating with this set of numbers I'm showing you with my mouse. Now we can take this set of numbers, the plus 0.22, the minus 0, the minus 3, and the minus 4.4, and we can dial them into what are called standard upper and lower limits for the hole and the shaft. And that's what these numbers are here on the input part of my spreadsheet. There's the nominal shaft diameter. And with these four sets of numbers, we're going to be able to figure out what are the minimum, maximum hole and shaft diameters. For example, the minimum hole diameter is still going to be 3.5 inches because it's 3.5 inches nominal hole, and it's a plus SL negative H, which is 0, so 3.5 plus 0 is 3.5. And the maximum hole diameter is 3.5022 because that's 3.5 plus 0022. The minimum shaft diameter is a 3.4956 inches because that's 3.5 inches plus a negative 0044. And the maximum shaft is 3.497 because that's 3.5 plus a negative 0.0030. The minimum clearance of 0030 is then d sub minus h minus d sub plus h, which is 3.5 minus 3.497. So it's basically the difference between the biggest shaft possible and the smallest hole. And that's 0030. And that translates here to our 3.0 times 0.0001 inches. And we calculate the maximum clearance as d sub plus h minus d sub minus s, which is 3.5022, the maximum hole diameter minus the minimum shaft, 3.4956, and we get 0.0066, which is our 6.6 number times 0.001 inch. ANSI ASME standard B4.1 specifies 5 interference classes of fits for mating parts. They go from FN1, the lightest interference fit, where only light pressure is required to assemble the mating parts. It's used for fragile parts and where no large forces are transmitted, all the way up to FN5, which is used for high-strength assemblies where super high resulting pressures are required. Our textbook gives you table 13-4 with all 5 classes of interference fits. You use the table similarly to the one for clearance fits, where you find your nominal size range, high and low, find out which row you're on, read across, decide which of the classes of fits you want to be in, and then it will tell you the limits of your interference as opposed to limits of clearance, and it will tell you how to dimension your holes and shafts. There is a gap in the table for FN3, mostly because people don't use FN3 for extremely small shafts and holes. Let's take a look at an interference fit for class FN1 with a nominal diameter of 0.1250 inches for the shaft and the hole. The minimum interference is 0.001 inches. The maximum interference is 0.006 inches. The hole size, therefore, is a 0.1250 plus 0.0003 inches and then minus 0. The shaft size of a 0.1254 inches comes from adding 0.0004 inches to 0.1250 inches, and the plus 0.002 tolerance comes from the difference between 0.6 and 0.4 times a 0.001 inches. We can compute pressures in components due to force fits. Figure 13-6 shows a bushing of inner radius A and outer radius B, and a sleeve of inner radius B and outer radius C, and the interference occurs at this mating surface between the sleeve and the bushing. The equations we have assume that the sleeve and bushing are made of different materials, and therefore we have a different modulus of elasticity for the inner and outer member, different Poisson's ratio. The pressure created by the force fit is shown here in equation 13-2. The pressure created by the force fit using two different materials is shown in equation 13-3. Note in equation 13-3, there is the modulus for the outer member, Poisson's ratio for the outer member, and the modulus for the inner member and Poisson's ratio for the inner member, where 13-2 assumed that the materials were the same, and hence there was only a one modulus and Poisson's ratio canceled out of the equation. We can also calculate the tensile stress in the outer member from equation 13-4. First you have to calculate the pressure, then you can calculate the tensile stress. And equation 13-5 tells us how to calculate the compressive stress in the inner member as a function of the pressure. Here's an example of how to use the equations. In problem 13-2, a bronze bushing is to be installed into a steel sleeve as indicated in figure 13-6. Here's figure 13-6. The bushing has an inside diameter of 2 inches, a nominal outside diameter of 2.5. The steel sleeve has a nominal inside diameter of 2.5 inches and an outside diameter of 3.5 inches. Specify the limits of size for the outside diameter of the bushing and the inside diameter of the sleeve in order to obtain a heavy dry fit, FN3, and determine the limits of interference that would result. Once we calculate the maximum interference, we are to compute the pressure that would be developed between the bushing and the sleeve, and the stress and deformation of the bushing and sleeve. And the problem gives us E equals 30 times 10 to 6 psi for steel, E equals 17 times 10 to the 6 for bronze, and use Poisson's ratio 0.27 for both materials. Using our interference table for class FN3 fit, we see that the nominal dimension B has a diameter of 2.5 inches, which is between 1.97 and 2.56 inches, so we're on this row here. And the total diametral interference is the worst case of the limits of interference. The limits of interference give us the smallest interference you could have, which is 1.3 times 0.001 inches, and the largest is a 3.2 times 0.001 inches. So we will use a 3.2 for the total diametral interference because that's the worst case. That gives us the highest pressures and the highest stresses. We use our formula to calculate the pressure, where A is equal to 1 inch, which is half of the 2-inch diameter. B is 1.25 inches, which is half of the 2.5-inch diameter. And C is 1.75 inches, which is half of its 3.5 inch diameter. In this case, the sleeve is made of steel and the bushing is made of bronze. Our textbook gives us a handy spreadsheet formula to use, which dials in the inner and outer radii and the modulus and Poisson's ratio for its input values. And using the equation shown here where my mouse is, you can calculate the pressure at the mating surface of 3518 psi. Tensile stress at the outer member is 10,846. The compressive stress in the inner member is a negative number because it's in compression, minus 16,025 psi. And the increase in diameter of the outer member is 0.00098 inches, and the decrease in diameter of the inner member is 0.00222 inches. They don't move the same amount because they're different materials. When you do a drawing, you can place standard tolerances within the drawing block, as shown down below. This drawing block says that if you go with 2 decimal places for your dimension, by default the tolerance is 0.03 inches. If you go with 3 decimal places, by default the tolerance is 0.010 inches. If you go with 4 decimal places, says the tolerance by default is 0.0005 inches. So it's a handy way to specify your tolerances without having to write them all out. Here on the upper right, we have different numbers to use based on the number of decimal places. But that saves you a lot of plus and minuses, and therefore you only have to give plus or minus tolerances when the numbers deviate from what is used in your drawing block. At some point in your career, you may use a geometric dimensioning and tolerance, and the point of that is to have certain dimensions in a part relate to other dimensions by virtue of form, profile, orientation, location, or runout. Examples of form are straightness and flatness and circularity. Examples of orientation are the angle that 2 dimensions make, or whether the 2 dimensions are perpendicular or parallel. A tolerance based on location can be either position or concentricity. Here's an example of how to use a geometric dimensioning and tolerancing for concentricity. You have a shaft that has several diameters on it. The left side has a large diameter, right side has a smaller diameter. And the datum is taken as the larger diameter, so that's what A means, datum A. And on this right side, we give a concentricity, that's the double circle, concentricity dimension for the smaller diameter, where we say that the smaller diameter needs to be concentric with respect to the larger diameter within 0.01 inches. Here's how you'd apply the various tolerances to drawings. You could put a flatness tolerance on a dimension. You could have a parallel tolerance between 2 edges. You could have a parallelism between the axis of 2 holes. Or you could have a perpendicularity dimension between one side of a part and another side of a part. And when all is said and done, you can do GD&T too on a drawing, and you will have a drawing that has a combination of numerical dimensions and then geometric tolerances which relate the dimensions.